Intelligence agencies today ingest millions of disparate points of data every single hour. Sensor readings, financial transactions, social media feeds. The sheer volume and velocity outpace any human team's capacity to process it. Hidden inside that noise are weak signals. These are subtle, low-visibility indicators, anomalous shipping patterns, minor code probes, shifts in diplomatic rhetoric that emerge right before a major geopolitical event or hybrid attack. Historically, intelligence organizations rely on horizon scanning, expert panels convened to analyze trends. But these human-centric methods are too slow for modern data streams and remain inherently vulnerable to cognitive biases like groupthink. We see a sharp contrast when we look at immediate tactical defense. Allied networks are highly efficient at identifying and neutralizing active cyber intrusions the moment a known firewall is breached. We are perfectly equipped to win the immediate tactical firefight. But without the ability to process weak signals at scale, we remain functionally blind to the broader strategic war forming on the horizon. A common institutional response is to assume that purchasing off-the-shelf commercial AI platforms will automatically fix this strategic deficit. Tools built for security operations centers are highly specialized. They excel at mapping specific network anomalies, but they struggle to synthesize long-term, multi-domain strategic warnings. Looking at this comparison of commercial platforms, the limitations become clear. They are optimized for low false positives in cyber environments, lacking the built-in cross-domain fusion required for strategic intelligence. To address this gap, researchers Kararslan and Stewart published a 2026 framework proposing a deliberate shift. Instead of relying on isolated commercial tools, they outline a dedicated multi-agent architecture. Anticipatory governance is a progressive data maturation pipeline that organizations must engineer from the ground up. This 5-layer model provides the blueprint for capturing and verifying subtle geopolitical shifts. Layer 1 begins with data acquisition. Every ingested sensor feed and open-source report receives an immutable chain of custody timestamp, ensuring full provenance for every piece of information. Moving down to Layer 2, the system deploys zero-shot large language models across this massive data foundation. These models do not search for known threat signatures. They hunt for statistical anomalies and semantic linkages across seemingly unrelated domains, operating without specific prior training examples. The output of this stage is categorized as S0, a raw, unverified candidate signal that requires immediate, deeper investigation. Stopping at S0 presents a severe risk. At this stage, the data is highly noisy, contextually blind, and riddled with false positives. Large language models are highly effective at finding needles in the data haystack, but they cannot determine if that needle is a weapon. We need an autonomous triage mechanism. That takes us to Layer 3, the multi-domain AI triage layer, which investigates the quality of the S0 candidate. Here, the architecture deploys agentic AI. These specialized autonomous coding agents cross-reference and pressure test the raw signal against a collaborative knowledge base. For instance, one specialized agent might verify unusual financial supply chain flows, while a completely separate agent simultaneously scans adversarial diplomatic rhetoric for matching timelines. If these independent agents corroborate the anomaly against historical baselines, the signal's credibility upgrades to S1. Layer 3 performs the critical function of taking a mere statistical anomaly and refining it into a credible, domain-verified intelligence threat. Next is Layer 4, the simulation layer, which provides the predictive capacity missing from traditional analysis. In a strategic context, a digital twin is a highly detailed, simulated representation of a critical physical system, like a port facility or power grid. By injecting the S1 intelligence signal into this digital twin, analysts model its causal linkages and observe the cascading, real-world effects in a safe environment. This simulation engine calculates the specific probabilities of various outcomes, maturing the intelligence one step further into an S2 signal. The simulation layer moves the intelligence process from monitoring what is happening right now to forecasting what will happen next. Finally, Layer 5 is the response layer, where the system delivers the finalized, decision-quality S3 output to strategic planners. If the system is this advanced, why does the architecture explicitly prevent the AI from executing fully automated strategic responses? While a human out-of-the-loop system operates with alluring speed, it carries unacceptable disadvantages in a geopolitical context, creating an accountability void and a severe risk of accidental escalation. A human in the loop is absolutely necessary to interpret political nuance, apply ethical reasoning, recognize strategic deception, and secure alliance consensus. AI serves as a high-recall filter and predictive simulator, but the burden of moral and strategic consequence must remain exclusively human. This table maps the 5-layer architecture directly onto the STEEP framework, providing early warning detection across social, technological, economic, environmental, and political domains. Multi-domain coverage is strictly required to detect virtual weapons, threats that operate in the ambiguous gray zone between baseline peace and overt warfare. Building this pipeline presents a critical engineering choice. Organizations must select between proprietary software and free open-source components. Relying entirely on proprietary solutions creates a severe strategic vulnerability, known as vendor lock-in. Defense organizations become inextricably dependent on a single corporate entity for their Foresight capabilities. In contrast, the free software approach listed here utilizes tools like Apache Spark, PyTorch, and Airflow. This guarantees institutional sovereignty, allows custom code modification, and prevents that dangerous dependency. To achieve true anticipatory governance, intelligence organizations must own their infrastructure, rather than simply renting it from a vendor. Implementing this 5-layer model moves defense agencies away from reactive alert monitoring toward interactive, defensible policy simulation. Intelligence architects, data scientists, and policy planners must debate and apply this blueprint to their own data pipelines to protect these high-level decision-makers. The framework presented here originates from the 2026 research text, Using Data Science Tools, a case study to identify weak signals. Artificial intelligence will process the raw terrain of the big data landscape, but it is rigorous, sovereign architectural design that will ultimately secure the future of the alliance.